Welcome to the webinar Sustainability in the EMAG Group on the way to green manufacturing with today's topic Energy Data Management. My name is Uwe Lachenwitzer and I work at EMAG in Saarlach as the Central Energy and Environmental Management Officer for the EMAG Group. I will guide you through the webinar today as the moderator. My colleague Johannes Röhring will then present the topic of energy data management in more detail. You are very welcome to ask any question about our chat function. Firstly, I would like to give you a brief overview of the industrial processes that need to be rethought. Typical challenge for sustainable production are: how do I optimize the product and material flow in my production? How do I understand and reduce the environmental impact of my production and supplier chain? How do I optimize my logistic network and industrial footprint to minimize environmental impact? How do I enable flexible and adaptable production? How do I plan for disposal, recycling, and reuse of byproducts? The final challenge: how do I get a company-wide overview of my energy consumption, will now be discussed by Johannes Röhring. Johannes, the stage is yours.
Hello, my name is Johannes Röhring. I am 22 years old and I am working as a project manager at our site in Zerbst for EMAG. My main department is process optimization and my main jobs are, for example, data analysis, process planning, IT consultation. But what I also do a lot is supporting our energy team and energy management with data analysis and with technical infrastructure. Let's talk about our site in Zerbst. Our site in Zerbst has the main task to be the central production hub for EMAG machines in Europe. Since 2013, EMAG Zerbst Maschinenfabrik has been pursuing the goal of continuously improving its energy efficiency, and the company's electricity consumption has been almost halved since 2013 by now. Okay, let's look at an aerial picture of our site. What we can pretty easily see is that we have around about 33,000 square meters of production space, at which we employ around about 460 employees. Our electricity usage goes in peak up to 1 megawatts. So when our factory is at full production, we take up to 1 megawatts from the grid. And to compensate for that, we decided to install a big photovoltaic system, which has a total capacity of 2.6 megawatts peak, which you can also see on the aerial picture on our factory roofs. Let's talk about that photovoltaic system for a bit. We have constructed it in 4 different stages, ranging from 450 to 750 kilowatts peak. We started in 2020 and ran the construction up to 2023. And 2023, so last year, we finished the completion of the last construction stage and now have up to 2.6 megawatts of solar power peak to our disposal whenever we have a lot of sun. In total, we have now generated up to 8.9 million kilowatt hours of solar energy. Just this year alone, we are already at 2.4 million kilowatt hours. That reduces our CO2 impact by a lot, and to date we have saved a total of 3.8 thousand tons of CO2 from our atmosphere. Okay, the background of my work actually comes from a different perspective, because for 10 years by now we already have an active energy management at our company, even before I started working. And in those 10 years, we have done all the low-hanging fruits, such as replacing our compressed air stations, improving our cooling systems, installing LED lighting, and the stuff that is generally done in energy management, which is kind of obvious or easily spottable by basic data analysis, such as looking at daily kilowatt-hour usages. However, after a few years, of course, when all the low-hanging fruits are done, you start to get more and more complex and start to see, okay, where can I even improve? And that is the point where we get to the measure, detect, save. And the main conspiracy is let data guide your decisions. You need to get into further data analysis to actually see more problems, more patterns, more than you easily see by just looking at daily readings. To get the data, we use several different sensors. For example, we use the Siemens electricity meter from the model Zentron PAC 2200 and PAC 4200. These were already present for our classic energy management before I started and are network-bound electricity meters. So you can easily read them through the network with Siemens' software or through different APIs. The difference between these two meters, aside from their current range, is mainly that the PAC 4200 also does grid analysis, stuff that we don't need for my kind of energy management. Our maintenance department, however, looks into those data a bit further than me. Okay. These meters actually have a Modbus TCP interface that we use to later read out the data. But at first, we want to see, okay, what kind of values do we even get? That starts with classic meanings as voltages, currents, apparent active and reactive powers, as well as power factors, the grid frequency, and the meter readings, telling us how many kilowatt hours have passed through the meter, so we can do hourly or daily analysis too of total meter readings. Once we found out that these meters had a Modbus TCP API, we of course need a software to read the data, and for that I decided for Node-RED. Node-RED is a software initially developed by IBM. It is a universal programming environment based on Node.js. It is fully open source and free, so it gathered quite a large community, which also provides a lot of different libraries and extensions and plugins that we are also using in our production to interface different components, such as, for example, the Siemens logo. All right. We are not only using Node-RED for data collection of energy meters, we also use it to handle data such as temperature data, weather stations, integrating into building control systems, building automation, data pipelines. Node-RED is really flexible for that. And once we get the data, we write it into a timescale DB, into a database. And once it's written into the database, we need to visualize it. For visualizing the data, we decided to continue the open source approach and picked Grafana as our main data hub. Grafana is a software that is fully browser-based, so the end user does not even need to install a software on their device. Everything they need on their phone or PC is just a simple web browser in order to see the data that we record. The software is fully open source, it is free, and has a large library of extensions and plugins, which we will be using in the later part of the webinar to see, okay, how can I get the most out of my data? Mainly, we visualize our data, for example, on our factory info screens. So our workers, even walking through a factory, can already see, okay, how much power are we using right now? How much power is our solar system making? How much did we make this month? Data that may interest them to just inspire them to look at energy data. Further than that, we have several dashboards, for example, for our management or for our works council, so they can observe different stuff. We will see that later. And we do a lot of detailed analysis on the data that may not be relevant for a simple employee, but that is the point where we actually start saving energy or generally finding potential to improve. Let's look at the first chart of the day. The first chart for us is an overview of how many sensors are online in our system. The graph currently has two red-colored fields. Those tell us, okay, something is wrong in the system right now. The screenshot was taken when one of our energy meters was offline of the network due to a small outage and is already colored red. Usually we have a total amount of 73 sensors online, consisting of 28 electricity meters, 6 gas meters, 29 temperature sensors, which also 17 of them give us humidity readings for the factory. We have a few weather stations and a lot of different sensors too, but the main ones are gas, electricity, and air temperature. Okay, let's go to the first dashboard of the day. This is our energy dashboard Zerbst, mainly made for our employees because it's the most simple display of our current energy data. We see the last 24 hours in history at the bottom, but the first part we will look at is the top area. On the left, we see our total power draw. That is the current value of how much energy is our production using. How much energy are the machines using in total, and the cooling systems and lighting and all together. And next to that, we see the total photovoltaic power. At that moment, we were only at 45 kilowatts because we were in the winter and really cloudy day. So there was not really much sun coming down And respective of that, we didn't cover our own usage entirely and had to buy in energy from the grid. And that is what we see on the right side. Our grid intake at that moment was at 491 kilowatts. So we took 491 kilowatts from the grid. Of course, if we have a lot of sun in the summer, that graph will go to the right side, to the positive area, and get green, telling us, okay, we're actively exporting energy and selling it to the grid, making money from that. Below that, we see 3 charts showing us the last 24 hours. The first one shows us the rightmost plot, telling us our grid intake or output over the last 24 hours. Actually, on the day beforehand, we see a small spike into the green area here. That is energy that we actually exported into the grid. After that, the red area tells us that at night, we, of course, took energy in from the grid because our solar system that we see below was at 0 watts during the night, since we can't make photovoltaic in the night. Below that, the last chart just simply tells us our power history of what the first chart told us, just in a timely manner. It is stacked in 4 different charts due to our different distribution stations, so you can see, okay, which part did actually take the most power. Let's get one step more complex. This is the next dashboard we are going to look at. It is our main monitoring board for our management and our works council. It not only consists of electricity data that is seen on the right side, it also has the 2 charts on the left side showing us the temperature data from our factory halls. Since we have temperature sensors installed at several workplaces to monitor the factory conditions and to see if temperatures in the winter don't get too low or in the summer don't get too high, and if they get too high, to give our workers an extra break or an extra timeout just so they can cool down again. All right, on the left side, we see the last 24 hours in a simple history chart telling us, okay, how warm was it in the factory and a current average reading. We're going to look at that later. For now, we're going to look at my own dashboards. I started with a simple monitoring dashboard just to check, okay, are all my sensors online? That is the first chart we saw on the very first slide, is here on the top right. In that moment, all sensors were online, so it's all green. On the bottom left, there is an empty area, which usually should also be empty. But if we have a sensor offline or a value that may have gone out of range, for example, a temperature dropping too low, then that raises alerts, and these alerts also get sent to my Telegram or to my Microsoft Teams account and will appear here on the dashboard, so you can easily see, okay, there is a fault condition, somebody needs to act on that data. I mentioned this is my old status board. That is because by now we have a lot more data. The system kind of escalated step by step. And I have actually reached a point where a simple HD monitor is not big enough anymore. And we decided, okay, let's get a big monitor for my office, a quite large full HD screen. And I made a big dashboard that shows me a lot of the data that I look at on a day-to-day basis. Most of my colleagues actually wouldn't fully understand the dashboard on a first glance. That is actually not relevant because in Grafana you can make highly specialized dashboards for the individual user. For me, the main relevant points are, of course, are all systems online. That is the small green chart in the bottom. I see electricity data, I see temperatures, I see gas usage, I see different separate electricity usages for example, compressed air, for our kitchen, for lighting systems. I see the outside temperature. There's a lot of data that I observe on a day-to-day basis just to stay on touch with production. And if something happens, for example, in production, I am probably one of the first ones that will actually spot it before even an alarm gets raised or a colleague complains about issues. Okay, we've looked at a few dashboards. Now we're going to look at a few charts and start with the simplest way to analyze data, with time-based or time series charts. What we see here is the last 7 days of electricity intake from our production. We see Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday. So in the center, we have the weekend where, of course, our electricity intake gets down a bit because production is not running. So we only have our standby loads. And then we can see that we ramped out production from Monday to Tuesday, and our electricity intake, of course, increases. Depending on how much production we have on a day-to-day basis, that value, of course, changes. For us, the most important part of this chart is if we just look at daily readings of kilowatt hours, we wouldn't see that we have a pretty high noise floor of standby loads on our production. And that is where the first point of data analysis comes in. With real-time dashboarding solutions, you're not just staring at an Excel spreadsheet. You can also see, okay, what is actually my standby load at the weekend, and see, is that normal? Do we have more than usual? But this is mainly done for a short time frame. I'm going to add one more point in this data, and that is the green line we see here now, which is our photovoltaic system and how much energy it made. We can see that on the weekend we had 2 pretty sunny days. The Saturday was pretty cloudy and the Sunday was a bright sunny day, which leads us to this beautiful bell curve. And the days before and afterwards, sadly, were pretty cloudy, which means, of course, we didn't make as much photovoltaic energy as we may have needed. And that is pretty obvious because the red chart shows us our usage and the green the production. So as long as the green line is just within the red chart, that is energy we have used ourselves. On the weekend, we have made so much energy that all that is above the red line has actually been sold to the grid because it was overproduction that we ourselves didn't need.
Oh, okay. Johannes, we have a question about this. And the question is, do you use storage systems for surplus energy?
Yes, we actually do. However, we're not storing electricity in its pure electric form, even when we have surplus electricity, because the main issue is with the amount of energy that we are using, since we are in the megawatt range, it is simply a big volume of power that needed to be stored. And against what we may have in a home battery system, for an industrial complex that gets expensive and big really fast. So we actually have decided against it and didn't install an electricity storage system. However, we have done different things. For example, for our changing rooms where we offer showers for our employees, we by now heat the water with gas during the normal day-to-day operations. But when we have photovoltaic power left over, so excess power, we actually disable the gas heating system and activate electric water heaters to heat up the water beforehand and to basically store the excess energy just in the form of heat. And we're planning to do that in several different steps too, for example, with cooling systems.
Okay, thank you.
All right. We have now looked at the very first chart and the most simple way to plot data, which can also probably be done in Excel if you want to do manual analysis. But we're now going to go a step way more complex. At the first point, this chart is a so-called Heatmap chart, may overwhelm the user in the first view. What we see here is a lot of data because the left side is in 2022, that is the year 2023, and that is the year 2024. From left to right, you see the last 2 years in photovoltaic production volume. Each column you see from left to right is 1 day. So each little pixel from left to right represents 1 day. And from the top to the bottom, we have the time range across the day. So each little pixel here is 15 minutes in real time. Each little block you have here is colored by the amount of energy that was produced in those 15 minutes. Just so you see the average amount of power. And then the color scale on the bottom tells us, okay, what does the red mean? In this case, an entirely red block means we have made 2.4 megawatts of power. So in the summertime, in the center of the year, of course, where the sun is at its highest point, our energy spikes up to the highest point. And in the morning hours and in the late hours, the energy amount goes down again. However, I mentioned our system gets up to 2.6 megawatts of production. We only need 1 megawatt for our own production. So let me recolor this chart and say, okay, everything that is above 1 megawatts of production will now already be red because that is everything we need. Everything that goes above that red range is sold to the grid anyways. And what we now see is that during the day in the summer, we have a lot of time where we have excess power. And in the winter times, that gets low pretty quick. And we don't have as much energy in the winter times. The thing that we can also see is that usually we start production at 6 a.m. The actual amount of power usually is present at 8 a.m. and does go quite deep into the evening hours. If we now compare that to our energy usage for our production, that is going to be a lot more cyclic because we have a 3-shift system. We have the morning shift from 6 to 15:15. We have the late shift going to nearly midnight, and when we have the morning shift, the night shift, that is done before the morning shift, before 6 a.m. We, of course, try to fit our usage mainly into the morning shift so we can use our photovoltaic energy more efficient. And you can see that from 6 a.m. to 15:15, our load is the highest, with 2 small gaps in the day range for the breakfast and for the lunch break. Because, of course, during lunch and breakfast, we turn off our lighting in the factory, so we save a lot more energy that way. And you can see that from the left to the right, there is a steady range that goes through where this gets brighter. That actually shows us the magic of a heat map chart, because with heat map charts, we were able to observe such patterns and also see anomalies in the data. Okay, let's look at our grid intake or grid output. That is now the difference between how much energy we produce and how much energy we use. If the chart is at a dark red, for example, in the winter time, that means we are actually buying energy from the grid. In this case, red means 1 megawatt being bought from the grid. However, the green side tells us we have overproduction. So the dark green area tells me we have actually injected more than 1 megawatt into the grid and covered our own energy usage beforehand. So if we look at this chart, we can see, of course, in the summer months, in the center of the year, we have a lot of energy production and a lot of excess power, which is to be expected. In the winter, we don't. The thing that is more surprising or more interesting, for example, for a management perspective, is look at the morning hours. From 6 a.m. to like 8 a.m. or even further to like 10 a.m. in the start of the year, you see, okay, we are buying energy from the grid. We are actively buying energy in for a pretty high price compared to what we get when we inject the excess energy into the grid, when we sell that energy later. And after the morning shift ends, after 15:15, we still have excess power. So our production need is earlier than what we actually produce with our solar system. And that means we're buying energy in the morning that we are selling later. And that is one of the challenges of energy management, to find ways to plan for it, to actually delay energy usage and to see how can I effectively use my excess power instead of potentially wasting it to the grid. All right, let us look at the next chart. This is also a heat map, in this case actually with heat data, with temperature data. I brought one of the examples of how our factory temperatures look. We see this nice green range in the daily range. In the week time, that green range means 19 to 20 degrees temperature at the workplace where we measured. However, this workplace only serves during the day shift and the late shift. The night shift is not occupied. So after the late shift, we actually reduce the factory temperature at that workplace to save gas usage. For comparison, 1 degree Celsius in temperature difference means 3 to 6% less or more gas usage. So just reducing the temperature at night and heating it up in the early morning hours is way more effective than letting the heating system run 24/7. And we were able to observe this with this heat map chart that it's actually working, because you see how the morning hours before 6 a.m. it slowly drops down the temperature and starts heating just around about 5:30, so the factory is warm when you need it. You can also see how long does my factory need to heat up. Based on outside temperature, you can maybe compare that and even adjust the preheating times, or in general see if you have issues. Speaking of issues, I actually brought a negative example of how it should not look. Because in this color scale, we see, okay, everything above 20 degrees slowly gets yellow to orange, and at 24, we reach a dark, deep red. And if we look at the left side, the first week, we see a lot of long red periods that go in the 2 to 3 hour time range, which means to us, okay, the factory actually heated up to above of 24 degrees and tried to keep that for several hours before it turned off again, cooled down pretty fast, and tried to heat again. And we wasted a lot of energy because the temperature was adjusted way too high. If you see 1 degree is 3 to 6% more gas usage, that is nearly 3 to 4 degrees that we saved. Because we saw those data, we then decided, okay, let's lower down the heating point. We did that in the second week and went to the nice green range, which was at that point acceptable for us. However, in the next week, we actually had a fault in the system where we only had one heater running. And after that, we decided to increase the target temperature of the factory floor more to like a 21 degree range, which is why it's going to be a bit red again. But what you see is we don't have those long red blocks anymore. We just have it in really short times, which means the system is now performing as expected. And that was one of the points where we actually found waste of energy being used and simply just optimizing our stuff. If you look at the same data in just a time-based chart, of course, you can somewhat see it in the top range that our system went way too high, but what you cannot really see is how many times did it switch. Did it actually heat a lot or did it switch pretty fast? And that is the magic of heat map charts, that you can analyze that pretty quickly. Okay, we talked about it and said we saved a lot of gas with it. How can I even say that? Of course, we need to monitor our gas usage for that. And I brought our gas usage with me. This is a chart that shows us an hourly distribution of gas usage. So each data point we have here is 1 hour of gas usage in total, plotted across a pretty wide range. And what you can see on the left here, that is actually the time between Christmas and New Year's Eve, where we shut down the factory and reduce our target temperature to 10 degrees. So of course, our heating usage of gas drops down quite a lot. What we can also see is these big spikes that come quite a lot. That is the first hour in the morning where we start up all the heating systems at once to get the temperature of the factory back up to speed. And after that, the gas usage, of course, drops to just continue to heat the factory. However, this does not really tell us how much were we actually using on that day. So let me change the interval to a daily measurement. So this tells us how much cubic meters of gas have we used per day. And we can see that the red line, that is our main gas usage, has quite a fluctuation in it. And now comes the challenge with energy data for heating. How do I know, did I actually use a lot of energy or was it simply needed because it was cold outside? And that is where the blue dotted line comes in. That is actually not gas usage. That is a number called heating degree days. This is an indicator for us, showing us, okay, how much energy should we have used to heat? Because the heating degree day number is based on the outside temperature, and the colder it gets outside, the higher the heating degree number goes. So if you simply put it next to your gas usage, you can actually see when our gas usage spiked, the heating degree number spiked too, and told us, okay, it was pretty cold outside. It's obvious that we needed a lot of gas to heat. What we can see in the further part of the chart is also the heating degree days fluctuated quite a bit, but our gas usage went lower and lower and lower because we started to implement optimizations with our temperature sensors, and that is how we can compare that we actually started saving gas or saving energy. And I can proudly say in the last 3 years, we have actually managed to reduce our gas usage by up to 30% by now, which is quite a significant number compared to what we have been using beforehand. Let's go to the next type of chart. This is called a so-called Sankey chart. A Sankey chart is mainly used to visualize energy or generally any kind of media flow in an entire system at one glance. So what we see here is our entire energy grid of my factory in one simple glance of a momentary perspective. So we see on the bottom left, those are our 4 different photovoltaic systems that in combination have a total power of 128 kilowatts at that moment because we didn't have that much sun. And our factory needed a total of 632 kilowatts. So, of course, we had to buy in from the grid. That is the top left part, telling us, okay, we needed 500 kilowatts of energy from the grid. And that distributes through the factory. We are going to remove the left side of the chart by now and just look at our energy usage aside from production. And we see our energy usage distributes across 5 different transformers. However, these transformers are combined in 3 different stations. So I just summed them up to see, okay, how much energy comes from which main part of the factory. And to the right of that, we see the different energy users that we measure. What we also see is we have quite a big block here that is not going anywhere. That is our unknown usage because we do not measure every single load in the factory. We focus on our significant energy users, our SEUs, which we measure, and those are, for example, our compressed air systems, our cooling systems, heating systems, as well as lighting and several different machines. And we can see here, the first 2 are big compressors. We also have a compressor here, and those in total get up to a value of 100 kilowatts of compressed air. Below that is our lighting system, in that moment 51 kilowatts. However, I have to say we do not measure every single lighting circuit. We only measure a few factory halls just for comparison. So our lighting usage is actually bigger than you see here. And we have a few different loads on the side there. If we really want to just see the simple side of, okay, are we actually buying energy or are we selling energy, we can look at this chart. On the top left, we see that we have the field of power intake. So that is externally bought energy. If we would have actually made more sun energy than we needed, then this would disappear and would appear at the bottom, showing us, okay, we actively sold energy to the grid. This was all momentary values now, so let us now look at a 30-day history, because one of the questions I get a lot from management is, after a weekend, I get the question, okay, why did we use more energy this weekend than last weekend? What took that much energy, and how can they know that it actually went there? And the thing I do is export a Sankey chart that tells me the history or the total and energy used. In this case, for the last 30 days, we can see, okay, we had a total usage of 236 megawatt hours, which distributed across our grid, of course. And in the end, 45 megawatt hours of that went to compressed air, and 16.7 megawatt hours went to lighting alone that we measured. So it is pretty easy to see, okay, how big of a part of our total intake is actually our compressed air, our lighting systems. And we were actually pretty surprised to see how much energy our lighting system draws, even though we installed LED lighting by now. So we already optimized it quite a lot. Let's now look at our gas system. Our gas system is a bit different than our electricity system because it's mainly in one big cascaded line. So our gas meters are actually sitting behind one another. The last one we have is our oven in our powder coating department, which is situated right behind the main meter of that department. Before that is the meter of the entire factory part, and the total factory you can see on the left, distributed so you can easily see, okay, just a small part on the right is actually going into production, into the oven. The rest that you see here is 90% all just heating. And in the summertime, of course, that chart mainly goes to one small line, and you can easily see if you have some gas draw anywhere else and observe that easily. Okay, I also brought an example of what we did to save a lot of energy, because simply spoken, pneumatic energy is one of the most expensive forms of energy you can have in your company, compressed air, because compressed air needs a lot of energy put into it to actually generate it. And we have 2 different air grids by us at our factory. And one of those 2 grids has a big advantage for me because it has no machines with sealing air. That means we don't have any air usage outside of the shift hours, or at least we shouldn't have. I looked at the data and was a bit curious and asked myself, hey, at night I have a consumption of 11.5 kilowatts. That is the nice green, light green range we have here. and asked around, okay, why is that? Do we have anything else behind that distribution board aside from the compressed air station? And found out, no, it isn't that case. So it has to be the compressor. The compressor was actually actively running, and I expected it to not have any output at all, but it had. So we walked around and looked, okay, where is the leak? Usually, monthly, we walk around with a sensor, with a device to check all the airlines and see if we have any leaks, but we didn't find anything. So the next step we did was walk around production during the end of shift and simply close off valves to isolate different parts of the factory and to see, okay, if I close off the circuit, does the energy usage drop? Because you can't simply look into the line. And after doing that for a few times, we actually found something. Our usage dropped down to 1.8 or rather 2 kilowatts. So that is a total difference of 9.7 kilowatts of leakage. Just to put that into perspective, a simple household energy socket in Europe can give you up to 3.6 kilowatts of total power. So where you plug in your toaster or anything at home, you can't get more than 3,600 watts out of that socket. This leak took up 3 times of that. 9.7 kilowatts of leakage can be compared to a 3-phase circuit of 16 amps running nearly under full load. And I asked myself, what was that leak? And I was actually pretty surprised because I thought, okay, it has to be quite a huge pipe that may have burst or something. No, it wasn't. It was a simple air hose, just like you use for compressed air nozzles or for air tools in your factory, which aren't even that big. It's like maybe 1 or 1.5 centimeters in diameter in the inside. That was running through a underground cable shaft, formerly to a machine. And that machine was disconnected once, and we guess that during the disconnection process, they didn't fully seal that hose, or it maybe got bitten by a rat. We didn't pull it out yet. We left it inside and just cut both ends off now. And that one hose had a total energy loss of 9.7 kilowatts permanently. And with permanently, I mean 365 days a year, 24 hours round the clock, doing shifts, out of shifts, which is a pretty significant amount. And just to see how significant it is, let us look at kilowatt hours. Even on a day-to-day basis, each day we wasted 232 kilowatt hours. And if we just look at the weekend, so Saturday to Sunday, that is already nearly 500 kilowatt hours. Just look at your own home and see how much energy are you using per month. And now compare that to this simple leak just on the weekend. The number is just gigantic. And if we look at a full week, we already escalate up to the megawatt hour level. We wasted 1.6 megawatt hours of energy per week, and per year that goes up to 85 megawatt hours. 85 megawatt hours is such a high number, and you have to consider that it's not just a one-time saving. You save this kind of energy every single year. And if you start to regularly check for leakages and find them based on data, that is not the only part that way you will save energy, because also you save a lot of money on maintenance fees for your compressed air stations. With that, I'm going to go to my conclusion. Our project clearly demonstrates how structured and thoughtful energy management can drive sustainable production. By utilizing modern technologies like Node-RED and Grafana, we were able to bring transparency to our energy flows and use this data for real-time decision-making. We are particularly proud of the sustainable savings we achieved. Major leaks were successfully identified and repaired, reducing waste and preserving valuable resources. A key part of our approach was involving our employees. By making energy data accessible and visible, we not only foster transparency, but also strengthen awareness of sustainable practices throughout the company. The use of open source tools like Node-RED and Grafana was a crucial success factor for us, because these tools enabled us to achieve maximum flexibility and innovation, even though we were on a pretty minimal budget, and had a clear win for both our efficiency and environmental goals. Through these efforts, we have established a solid foundation to further reduce our industrial footprint and advance green manufacturing at EMAG.
Okay, Johannes, thank you very much for your great presentation. We have now 2 more questions from the chat. The first one, is it possible to adapt the concept of EMAC to other companies? And the second one, how are employees involved in energy data management?
Thank you for the questions. For the first one, is it possible to adapt the concept of EMAC to other companies? Yes, it is. Not just for other companies, even for private homes. The concept is pretty simple. Since we used open source tools for the entire chain of the process, aside from the hardware, getting started with it is pretty easy, pretty cheap, compared to different systems such as, for example, the Siemens Power Manager, which may have a big upfront cost. However, the main part for me that I have to advise everyone to do is don't just look at daily meter readings and see, okay, how much energy do they use per day? Start recording the data for the entire days and look at 15-minute intervals, look at Heatmap charts and get to know your usage. See when do you take energy, how much do you take at the weekends, how much do you take at night, and find all the waste and eliminate it. The second question, how are employees involved in energy data management? I mentioned that at the start of my presentation. In total, our energy management confronts our worker at the very first moment they enter the factory. Through the very first info screen we have, we already show them how much energy are we using right now, how much photovoltaic are we generating right now, even without them actively going to like a dashboard on the internet or intranet. However, they are able to look at the data themselves through our intranet, through our dashboards, and even going beyond that, we actively talk with our employees about the energy data. For example, in the wintertime, when gates were left open and we had energy losses due to temperature fall downs, we were able to take out the data from Grafana, show it to the employees, and actually show them how much energy did we waste in that, and just sensitize them to think about what does your actions have for a footprint and how to improve on that without maybe accusing them or something. Just simply explaining them the data is the best part you can do.
Thank you very much. And now stay brave and motivate. In this sense, we both say thank you very much for your participation in the webinar and wish you and your family a Merry Christmas and a good start into the new year. Goodbye.